Hi guys, in this video we are going to find out the moment of inertia of a thin uniform rod about two axes. One axis which passes through the center of the rod and is perpendicular to the rod, which I have marked as Z in the figure, and the second about an axis which passes through any one of the ends of the rod. So here we are taking the entire mass of the thin uniform rod as capital M, and the total length is taken as small m. So here we are defining a quantity called the linear mass density. Linear mass density, which is represented by small m, which is the mass, total mass per the entire length, which is the mass per unit length of the thin rod, which is the linear mass density. Now, in order to find the moment of inertia, we are considering a small element of the rod like this, of length dy, which is at a distance y from the center, which means the mass element under consideration here, it is at a distance y from the z axis. So now we have to find, in order to find the moment of inertia of this mass element, we have to first find the mass of the mass element. So the mass of the element of rod, which we will represent as dm, is equal to the mass per unit length small m into the length of the element, which is dy. Now the moment of inertia of this mass element, inertia of mass element, is equal to the mass of the element dm into the square of the distance, and the distance here is y, so y square. Now in order to find the moment of inertia of this entire rod, you have to integrate it along the length of the rod. Moment of inertia of entire rod, I is equal to integral dm into y square. And since we are integrating this element along its length, so the element, it can be either on this side of the rod or this side of the rod. So in this side the length varies from 0 to L by 2, since L is the total length, and towards this side the length varies from 0 to minus L by 2. So the integration limit here is minus L by 2 to plus L by 2. Substituting for dm here, you can write it as m dy into y square integral minus L by 2 to L by 2. And since y square here, it is an even function, you can write this integral as 2 into integral 0 to L by 2 my square dy. On solving this, you will get 2m y cube divided by 3. Applying the integration limits for y, you will get this as 2 by 3 m into L cube by 8, which is m L cube by 12. Now you have got the moment of inertia in terms of small m. Now in order to find the moment of inertia in terms of capital M, you have to substitute for small m here, which is m by L into L cube by 12, which is ml square by 12. This is the moment of inertia of the thin rod about an axis which passes through the center and is perpendicular to the length of the rod. Now finding out the moment of inertia about the axis through the end of the rod, we already know that the moment of inertia about this z axis is I is equal to ml square by 12. This we can write it as I center of mass, because this is a uniform rod and O is at the exact center of the rod. So in order to find this moment of inertia, we can use the parallel axis theorem. So using parallel axis theorem, the moment of inertia about this axis I is equal to we have the moment of inertia about this axis, which is ICM, plus since this axis is parallel to the center of mass axis, you can add a term called the mass into the square of the distance between these two axes. Here the mass is capital M and the square, the distance here is L by 2, so you can multiply L square by 4. Here substituting for ICM, ml square by 12 plus ml square by 4, which you will get as ml square by 3, which will give you the moment of inertia of this thin rod through any of the one end of the rod.